He works for CompPair technology, and he will present us something about self-healing material. I mean, we talk about recycling, but the best thing is we do not need to recycle material because it's self-healing and we can reuse it. So I'm looking forward to see what you will present us today.
Thank you very much, and good afternoon to everyone. Actually, we had the last-minute change, so it's not Robin Triguera. Robin is my partner, but my name is Amael, and I'm CEO of the company. So today what I'm going to present you is, of course, what we're doing at CompPair, but also the strategy that we did put in place to reach also those composites and towards circular economy of the industry. And the strategy that we're applying, which is totally in line with our vision, is to really try to bring this full circularity to the composites industry. We know that there will be damage to composites, and that damage will be either to the matrix. With our products, you will see that we can heal. And if damage is too big to the fibers, we're not claiming that we can do much, but we will be able to recycle, closing the loop. And such circular economy model has demonstrated the potential to save up to 50% of composite resources. This is totally in line with the UN SDGs and has the potential to save megatons of CO2 emissions. So just to be clear, the problem that we are answering here, and I've seen that through many of the presentations also those 2 last days, is on the side of design and how can we design, how can we change the base materials to bring also more sustainability and reach a strategy of circularity. And here we are reaching the problems of sensitivity to damage, which on one side, for many applications and structural application, we start to do the patch repair mechanism that you know, which is cumbersome, which takes a lot of time. And for many other applications, we just decide to replace parts, generating a very high amount of unrecycled waste. And you know that composites nowadays, 90% of them are recycled. So the solution that we are bringing with CompPair is really a new composite material that is able to repair itself and be better recycled. And how do we do that? You will see our products are prepregs, and they are sold as raw, like traditional prepregs, to build healable composites. And specifically, those new composites have the capacity to be repaired 400 times faster than traditional composites, the capacity to be regenerated fully, multiple times, and at the end of life, an efficient recycling. I will come back to that as well. Something that was really important for us, and you know that we have been talking about self-healing composites for many years right now. There were many research as well, and we are coming from EPFL in Switzerland. There were 3-4 PhD theses before mine, and we had always the strategy of bringing fully autonomous repaired composites. Here we change a bit the strategy by saying, okay, let's trigger the healing by heat, but at room temperature, we stay structural and we provide good mechanical properties. And actually, this was the right strategy because now we are able to bring those new functionalities, but while having a compatible production. This is something that is really important for us as well, for all the product families that we are developing, and crack resistance and mechanical properties that are competitive. So to show you how it works, there is the small video I hope that we will see, but we had a live demo, and I know that most of you have seen the live demo on the booth as well. So that's a typical aerospace part that we impacted, and in the middle of the screen there, you can see a typical damage, around 20 millimeters in diameter. If we were to use the traditional patch repair mechanism, it will take 5 to 6 hours. Here, we just come with a heat gun, 100 degrees or 150 degrees for 1 minute, and it's over. We recover all the initial mechanical properties. So no need to apply pressure, no need to put back the part into a mold into there. How do we bring such technology onto the market and how we did it? It's through our first product into the portfolio called HealTech. We have a production capacity now at industrial scale, even though we are a young company. And the opportunity with us is to really provide the product portfolio extension. We have this first product into the portfolio, but we are bringing other product families with different cycle times, different cure temperatures to really have a complete portfolio adapted to many different types of applications. And including into there, we include recycled fibers and natural fibers. We have some small parts on the booth as well to show. And this is really in line with our vision of circular economy as well. Specifically, our references here, and those are the commercial ones, 3, actually 4 in carbon and 3 in glass, and all those products have received the label of the Solar Impulse Foundation, which was for us really important because they were experts that assessed our solution in terms of ecologically efficient and economically efficient as well. We have seen before some demonstrations visually with impact that you see with the demonstration that we have on the booth as well, but how does it stand also mechanically? And this is what is important as well. This is a typical test that we like to have and that we propose as well to our customers to show the damage. And coming from also the self-healing field and for many years of research, when we are providing self-healing strategies to composites, we cannot reach the fibers. If we reach the fibers, we are not repairing them. So we need also some specific testing to show real-life conditions, and a static test in a lab is not really representative of what will happen into real life. And so here, this test shows bending on a specific layer where you damage the matrix specifically for a virgin material, so without any damage. For a damaged material, you see that the mechanical properties are reduced, and for a damaged and healed one, where you see that we recover the mechanical properties. What we can do is exactly the same for fatigue testing, where we came on the part and we really cycled many times, actually 20,000 in this case. And what you see is that we've done that for HealTech, and each of the vertical lines is one helix cycle. So with our composites, each time we regenerate, we can start again, whereas for standard composites, for the same layup, and this was a standard thermoset-based composites, you see that the damage continues and then the part breaks. We can go for larger types of damage, maybe small impacts that will come, and we can recuperate the entire damage as well. We've confirmed that also through non-destructive testing. We have that internally into the company as well if needed, and we're doing some macroscopy analysis. So just a few examples to show that there are many ways where we can assess damage and where we can assess healing as well. It will really depend on the application and on the potential also of different applications, different customers, etc. One interest as well with those materials is damping properties. What we have seen is that there is, depending on what frequency we use, but a higher damping potential. And this is also for many applications, specifically in the sporting goods, and I will come back to that, is of interest. Before, we have spoken about mechanical properties, and also what I said is that for us, it's really important to bring mechanical properties that are in line with benchmark. Of course, it depends to what you compare to. If we are getting the comparison with ultra-high modulus and performances for resin into the space domain, for some of them, we are not competitive at all, but we have strategies to do that. But if you look at the benchmark and really traditional one, we are really meeting those benchmark, and those are ranges on this graph. And for crack resistance, so toughness, we are in average 30% higher than what you may find for traditional composites. We have seen here regeneration, different types of healing mechanisms through different tests as well. And something that was really important for us, and here I'm shifting a bit out of the company as well, but throughout the assessment of those self-healing technologies, of those healable composites, what are the benefits behind? Because we have seen great features right before, but what are the benefits really specifically onto the market? And here, I'm not going to go into too much details, but we can discuss that after the presentation if you want. But that's something that we have worked with the entire team a lot for providing the benefits at two levels into the value chain, the level where we produce composites, and what are the benefits here, and the level where we use those composites. Because actually, those prepregs that we provide have an improved operational efficiency for several reasons, but because they have a 60 days work life, they have a low exotherm, so that's of interest. They can be processed really nicely out of autoclave. And then because there is regeneration, because the cure cycle is at 140 degrees and we heal already before, out of the production, you can have for certain types of applications already reduced porosity and reduced internal stress, and I'm going to give an example right after as well. For some example as well, where you have maybe the production of a part from a warehouse and then you need to bring it to another. You may have damage as well during this transport or different types of damage that can appear before delivering the part to your customer. This can have also some repair cost, and we have seen with an example that I will give after as well, specifically that there is a really nice also reduction for the production repair cost reduction. We go to the second level, which is the lifetime benefits of the composites, and this is constant properties, first of all. We have seen before by regeneration, downtime reduction for certain applications where we have as well also we need to produce, for example, electricity, and this is problematic if we need to shut down, for example, a wind blade, and then we need to repair it, and it cannot produce electricity. Healing more generally, and at the end of life, and this is the interesting one, is as well recycling. We have demonstrated with those composites a higher propensity for being recycled and reaching really a positive level of CO2 footprint. And what we are doing throughout the entire life cycle as well of those composites is provide some clear life cycle analysis to our products and to the applications that we are performing to show the benefits of CompPair technology as compared to the current state. So a few examples on the improved operational efficiency and all those elements that we have seen before. There were the work life, as we have mentioned before, the improved machinability as well. We have worked with a partner company to have a report on that one and to show that the machinability is easy and for some applications more efficient with traditional tools that you may use. In terms of internal stresses as well, what you see here is typically we've played around with really asymmetric layups, and out of the production you have really the composite that is completely bended. But what you see with CompPair composites is that this is reduced. And this is of interest because we reduce the internal stresses into there. We've mentioned production repair cost reduction before, and this was the example I was mentioning on foam sandwich panels, and this is also of interest if you're playing with the right foam and the right interface as well. You can really recover large dents, 50 millimeters in that case, and this was typically for a boat manufacturer in France who was spending in average 2 days to repair such kind of damage, and using our products, it's not 2 days anymore, it's just 2 minutes. We have the downtime reduction, and this is another video to show you that it works also on other type of parts or other geometries as well, where we impact. You see a typical impact here really on the edge, and we come again the same as before, and we just heal for 1 minute, and you will see that the damage will completely disappear right after into there. Of course, here, and that's coming back as well to what we have mentioned before with carbon, and here we see it on glass, so it's easy because it's transparent, but with carbon, what we see is there is the interest either of mechanical properties or of non-destructive testing assessment. Healing benefits, and I was speaking about LCA analysis before, what we have done, and you will say, yeah, that's normal that we have this drastic decrease, that's for sure. And what we have done is trying to quantify as well the benefits of healing as compared to replacing or the traditional repair. And of course, it's dependent on the scenarios that we have taken, on the hypothesis that we have taken, but here what you see is that in terms of kilograms of CO2 equivalent for reproduction of a composite or repair of a composite or repair with just the 1 minute with the heat gun, which is basically here what we need is to repair with the heat gun, you see that there is a drastic decrease. I will hurry up. On the side of recycling, I was mentioning that before, we had a really great demonstration with a company called Decathlon, sports equipment manufacturer in France, and what they did was to take our products, produce a part, and then send it back to us. We have recycled with our facilities at small scale for now, and then send back the products, and what they could do is a new product with 87% of recycled fibers. And this is totally in line with the 3R circular economy strategy that we are applying: reduce, reuse, recycle, with all the elements that I was mentioning before, and especially using as well recycled fibers, but also bio-based resins. Where are we applying this technology? For 3 different, let's say, market verticals: leisure, wind, and aerospace. Wind specifically, we have a project to bring this technology towards infusion, and next month there will be a great demonstration around that. So here it's towards infusion, and the 2 others are with prepregs. Winter sports, I'm going to skip this one, but this was the interest for winter sports as well on wood cores, and specifically the demonstration that we have done with the ski case, with Salomon, showing a 20% CO2 emission reduction by getting life cycle analysis comparison between their current state and what we're doing at CompPair. The gunboat case is the one that I was mentioning before, with drastic reduction of repair time. And finally, we have some activities as well into the space industry. Recent announcement as well with Ariane Group on a project that we are pursuing. Really shortly, we are a young company. This is actually based on my PhD thesis, and we started the company here in 2020 with Robin, and we could scale up the company, and now reaching 2022 with first commercial implementations and with the upscale of this production, and also behind with a great team. I'm not alone. We have 20+ collaborators working on CompPair, and we feel free to contact us for any requests. We are open to any potential applications. Of course, we have our verticals of interest that we have assessed, but for any other types of application, we are always interested to bring more circularity to this composites industry, and thanks to the use of our products. So with that, I hope that you will join us on this impactful journey. I thank you very much for your attention, and happy to answer any questions.
Yeah, thank you for this presentation. And in this case, in a field I'm familiar with, because composites and not steel. Are there any questions? Bastian. Please, use the microphone, you know it.
Yes, thank you very, very much for this, I think, great presentation. I mean, obviously your magic is in the matrix, right? And I know you won't tell us the chemistry, but can you share some details about it? You said shelf life 60 days, so it's a thermoset, I assume. But is it? Can I reshape to a certain extent as well if I heat it up? Is it connected?
It's a thermoset-based material, and this is the interest here of not having the need to put it back into a mold to apply pressure for getting back the mechanical properties and regenerating the damage. To a certain extent, yes, you can reshape, because when we're heating, of course, there is a part of the matrix, a healing agent specifically, and that's our magic that gets activated to enable the repair of the cracks. And into there, what we always say is that there is, let's say, around 20% of elastic properties that are reduced, but that's normal because you increase slightly the temperature and there is disactivation. And this enables part of, let's say, reshape, but to a certain extent. So it really depends on your application. For some of the applications, on some examples that you have seen throughout this presentation, this works well. For some others, if you want to reshape completely, it will not work, that's for sure.
Thank you.
Okay, are there any other questions? If not, I have one was already the same question, but I have an additional question. The temperature area you can use it. So say it's for the repair, you use the temperature between 100 and 150 degrees. So, but how high can get your temperature with the normal properties of your material, or will the properties go down?
What is important to know, and that's really interesting case, is the fact that this is thermoset based. So the TG of those materials is between 140 and 180, let's say, depending on the cure or post-cure that you do. But before, as there is this activation, there is a decrease of mechanical properties, but it all depends on your applications and what you need, because what people are used to is to have the room temperature data, and then after the TG, where you drop usually to 0. Whereas here we activate and you are somewhere in the middle or somewhere slightly higher than the middle, and you have still structurality of the parts. So it all depends on your application and what you need. For some of the applications where you are, what we say is that you do not need to go above 80 degrees for, let's say, service temperature. But again, that's also our core knowledge to develop other chemistries, and this will come to have higher service temperature materials. So we are working on that one, and if some people like also to join such kind of projects, we are happy to discuss.
Okay. Okay, one more question?
Is it working?
Yeah.
Yeah. Thank you for sharing your stories. I have a question. What we saw in the movies is just a visual appearance, the surface that sort of changes while you see it. Is the visual appearance the only thing how you can control either the damage or the repair of it, or is there other means of controlling the repair process?
On the final, it all depends again on the application, but some of the examples that I have shown throughout bending tests, so in static test where you see the recovery of the damage and the repair, or the fatigue as well, you see it clearly through mechanical assessment, and that's always what we're looking at. We have done compression after impact test as well, and we see also the repair potential. Interestingly, with the compression after impact that you all know, we were going to fiber damage as well, and what we see is that even if there is fiber damage, the most important is to recuperate the load transfer between the layers. And so even if you have some fibers that are damaged, we recuperate usually between 50 and 80% of the original properties in compression, so that's really nice as well. Then it depends on your application, and that's what we say. I did not show it here, but we like also in our company to be here to join the customer and to work with them to assess the case and see where we can support with our expertise of repair. Because it will depend. We can do customized tests as well for them, and some of the sports example that I've shown before, we did really go all the way with the customers to design a specific test for them, specific for the application and adapted to the application to show the repair, let's say, value for them. Hope that answers your question.
Okay, one more question. And due to the last presentation, I think we have some time for all these questions.
Does it work? Yeah. Thanks for your interesting presentation. I got a question to the damage size. So what you showed is comparably low damage area. And did you figure out a limit where it's still repairable? Or can you say something about it, how big the deformation or the impact area can be?
So in terms of impact area, as long as you do not reach above a certain thickness, then it's fine. But it's more on the side of thickness of the damage. So if you have two layers that are like open, like a mode 1 DCB test, you know, this will not work, of course. But as long as you stay really with small delaminations in the order of 100 microns, then this will work. And this is the start, This is the start, and this is what we have always seen, is that these are the small damage that will grow until catastrophic failure. And this, we want really to act at the beginning of this damage problem, let's say.
Okay, are there any more questions? You're welcome. If not, then thanks again.
Thank you
For your great presentation.